In this video we're going to look at some more statics problems. Now the key thing to remember is that if a rigid body is in equilibrium, then the resultant force must be equal to 0 and the resultant force about the resultant moment about any point must be equal to 0. And we will normally rewrite this condition by saying that the anticlockwise moments about any point must equal the clockwise moments about the same point. As a general rule, there are three different ways that we can attack problems. We can either resolve the forces in two directions and take moments about one point, or we can resolve the forces in one direction and take moments about 2 points, or we could take moments about 3 different points which should not lie on a straight line. Generally speaking, I find the first of these three methods as being the most useful one. And you'll find that in the examples that we're going to be doing in the course of this video, we'll use that as the general process. So let's have a look at our first example. A rod AB of length 6 meters and weight 300 newtons is freely hinged to a vertical wall at A. It is held in a horizontal position by a light inextensible string BD, where D is a point 2.5 meters vertically above A. Particle of weight 150 newtons is attached to the rod at C, where BC is 2 meters. We've got to calculate the tension in the string and find the magnitude and direction of the force exerted by the hinge on the rod. So we need a diagram clearly to start with. So there's my diagram. First bit is there's a little bit of trigonometry that we can do, because we're certainly going to need some angles when we come around to doing some resolving. So if we call the angle theta being the angle between the rod and the string, then we've got tan theta is 2.5 divided by 6, so theta is 22.62 degrees. We need to add some forces to our diagram. So we've got the weight of the rod, and since the rod is uniform, the weight of the rod is going to be acting at the centre of mass of the rod, which is going to be at the middle of the rod. We've then got the force that C exerts onto the rod, which is going to be a force of 150 newtons. We've got the tension in the string. And finally, we've got the reaction at the hinge. Now, in previous videos, we saw that generally speaking, it's a good idea to express this reaction at a hinge as being two components, one in the horizontal direction and one in the y direction, rather than having it as an unknown force at an unknown angle. So we'll have the reaction at the hinge being x horizontally and y vertically. So now resolving, first of all vertically, I've got y plus t sine theta minus 300 minus 150 must equal 0. In other words, I've got y plus t sine theta must equal 450. Resolving horizontally, we've got x minus t cos theta must equal 0. In other words, x must equal t cos theta. And now, having resolved in two directions, I need to take moments about 1 point. The sensible point to take moments about are A or B. Using B makes life slightly easier because T has no moment about B. X has no moment about B, and then the forces Y, the 300 and the 150 are very easy to do the moments for. So we're going to take moments about the point B. The clockwise moment is provided by Y and is going to be Y times 6. The anti-clockwise moments are going to be provided by the 300 and the 150. The anti-clockwise moment of the 300 is going to be 300 times by 3, and the anti-clockwise moment of the 150 is going to be 150 times by 2. So taking moments about B, we have anti-clockwise equals clockwise, so y times 6 equals 300 times 3 plus 150 times 2, which tells me that y, or 6y, must be 1200. In other words, y must be 200 newtons. Now, there's the working we've done so far. If we go back to equation 1 now, we've got t sine theta is 450 take away y, which means that t sine theta must be equal to 250. So we've got t is 250 divided by the sine of 22.62 degrees, which gives me 650 newtons. And then equation 2 gives me x equals t cos theta. In other words, x is t cos 22.62, and that becomes 600 newtons. So I can now draw a picture to represent the reaction at the hinge A. The reaction at the hinge A has got a horizontal component of 600 newtons to the right and a vertical component of 200 newtons vertically upwards. So the reaction has magnitude of the square root of 600 squared plus 200 squared, which is 632.5 newtons, and makes an angle of alpha, which satisfies tan alpha is 200 divided by 600. In other words, alpha is 18.4 degrees above the horizontal. So, a second example now, we've got a uniform T-shaped lamina. It's made consisting of a rectangle of length 10A and width 2A, together with a rectangle of length 6A and length 2A, as shown in the diagram. Point A is the point 2A 0, and the point B is the point 0, 12A. Are corners of the lamina, and we've got to prove that the centre of mass is the point 3A, 29 over 4A. Now the first thing to notice about this T-shaped lamina is that it's got a line of symmetry, which is x equals 3A. So therefore the x-coordinate of the centre of mass must be 3A. To find the y-coordinate of the centre of mass, we need to split the lamina into two components. So we'll take the bottom part of the T-shape together with the top part of the T-shape. The bottom part of the T-shape has got an area of 20A squared, so its mass is going to be 20A squared times by sigma, where sigma is the surface density of the lamina. The centre of mass of this bottom part is going to have a y-coordinate of 5A, so the sum of the my's for the bottom coordinate for the bottom component is going to be 100A cubed sigma. For the top of the T-shape, we have a shape of area 12A squared, so the mass is going to be 12A squared sigma. The y-coordinate of the centre of the mass is going to be 10A plus A, in other words 11A, and therefore the sum of the my's for the top of the T-shape is going to be 12A squared sigma times 11A, which is 132A cubed sigma. So for the whole shape, we have a shape of mass 32A squared sigma, and the sum of the my's for the whole shape is 232A cubed sigma. So the y coordinate of the centre of mass is going to be the sum of the my's for the whole shape divided by the mass of the whole shape, which is 232a cubed sigma divided by 32a squared sigma, which cancels down to give me 29 over 4 times by a, and therefore the centre of mass is the point 3a, 29 over 4a. Initially, we're told the lamina is hung from a ceiling by two vertical strings, one attached to A and one attached to B. The axis of the lamina is now horizontal. If the weight of the lamina is W newtons, we have to calculate the tension in each of the strings. So let's add the forces onto the diagram. We've got the weight acting at the centre of mass, which we know is 29 upon 4a up the T shape. We've got the tension in A, and we've got a different tension in the string at B. So, resolving vertically, I've got T plus S minus W must equal 0. Which tells me that T plus S must equal W. And if I take moments about the point A, then the clockwise moments must equal the anti-clockwise moment. W is trying to turn the T shape in a clockwise direction, so we've got a clockwise moment of W times by 29 over 4A must equal S times by 12A. In other words, we've got S is 29 over 48 W, which then tells me that T must be 19 over 48 W. If the string linking A to the ceiling is cut, then the equilibrium position of the lamina is such that the line of symmetry of the lamina makes an angle alpha with the vertical. We've got to calculate the value of tan alpha. So we need a diagram to do this again. So here is a diagram showing the situation just after the string connecting A to the ceiling has been cut. So the line of symmetry is still horizontal, and we can mark the centre of mass as a point on that line of symmetry. Now critically, we know that when the T shape settles down in equilibrium, the centre of mass will be vertically below the point B, so the line joining B to the centre of mass will become our vertical line, and the angle that we're trying to find is the angle between the vertical and the line of symmetry of the T shape, which is the angle alpha there. Now, if we remember the coordinate system that we were using for this particular problem, B was the point 0 to 12a, and we managed to show that the centre of mass had to be the point 3a, 29 over 4a. So that means that in moving from B to the centre of mass, in the x direction I'm going to have to move 3a, and in the y direction I'm going to have to move a distance of 12a, take away 29 over 4a, which is 19 over 4a. So I can now say that tan alpha is 3a over 19 over 4a. In other words, tan alpha is 12/19. And our final example shows a straight uniform rod of weight 1400 newtons and length 4 meters, resting in equilibrium with its end A on rough horizontal ground. A light cable which is attached to the other end B is holding the rod with the end B off the ground, so that the rod makes an angle of 20 degrees with the ground. the cable is making an angle of theta with the horizontal. If the coefficient of friction between the end A and the ground is 0.6 and the end A is about to slip, we have to calculate the normal reaction of the ground on the rod at A and the tension in the cable and the angle theta. So clearly the first thing we must do is add some forces to the diagram. So we've got the weight acting at the midpoint of AB. We have the reaction at A. We've got the frictional force F. And we have the tension T. So, resolving vertically, we've got R plus T sine theta minus 1400 must equal 0, or R plus T sine theta equals 1400. Resolving horizontally, we've got T cos theta minus F equals 0. Since we've got limiting equilibrium, we've got F must equal 0.6 times R. Now the fact it's limiting equilibrium is because we've been told that the end A is about to slip. So I know that F is equal to 0.6 R, so we can rewrite the previous equation as T cos theta minus 0.6 R is equal to 0. And we're going to need to take moments about a point. Now, in this case, the easiest point to take the moments about is the point B, because that means that I won't get theta occurring in the equation and have any really awkward bits to deal with. So, taking moments about B, we've got the clockwise moments about B must equal the anti-clockwise moments about B. The moment of R about B, well, first of all, R is trying to turn the rod clockwise about B. The distance of the line of action of R away from B is the horizontal distance between A and B, which is 4 cos 20. So we've got a moment of R times by 4 cos 20 in a clockwise direction. F is also trying to turn the rod in a clockwise direction about the point B. The distance of the line of action of F away from B is the distance of B above the ground, which is 4 sine 20. So the moment of F about B is going to be F times 4 sine 20. And then for the anti-clockwise moment, well, the anti-clockwise moment is produced by the 1400 newtons, which is trying to turn the rod anti-clockwise about the point B. And the 1400 newtons, the line of action of the 1400 newtons is a distance which is half of the horizontal distance from A to B, so that is going to be 2 times cos 20. So the anti-clockwise moment is going to be 1400 times by 2 cos 20. We know that F is 0.6 R, so we can rewrite the left hand side as 4 cos 20 times R plus 4 sine 20 times by 0.6 R, and that has to equal 2631.1. In other words, we've got R times by 4 cos 20 plus 2.4 sine 20 must equal 2631.1, which gives me R equals 574.5 newtons, and F is 0.6 times R, so that's 344.7 newtons. So we've found the normal reaction, we've still got T to find. So if we look at equation 1, And equation 1 now tells me that r plus t sine theta is 1400, so that's 574.5 plus t sine theta equals 1400, so t sine theta must equal 825.5. Equation 2 tells me that t cos theta minus r must equal minus 0.6r must equal 0. So that's t cos theta must equal 344.7. So if I now square and add equation 3 and 4, I'm going to get 825.5 squared plus 344.7 squared is t squared sine squared theta plus t squared cos squared theta, which is the same thing as t squared times sine squared theta plus cos squared theta, which is the same thing as t squared. So I've got t squared is 825.5 squared plus 344.7 squared, so t must be the square root of 825.5 squared plus 344.7 squared, which is 894.6 newtons. I know that t sine theta has got to equal 825.5, so I've now got sine theta is 825.5 divided by t, which is 825.5 divided by 894.6, so theta must be 67.3 degrees. And that concludes our look at 3 typical statics type problems.